Hello everyone, and welcome to a new session on application of moving load in STAAD. I am Surajit Ghosh, and in this video, I will discuss how we can include a horizontal and axial load component along with a vertical moving load and combine it with other primary load case. For complete design of any warehouse or industrial structure with overhead crane, we need to combine the crane load with other load to find the worst effect. How we can combine a moving crane load with other gravity and lateral load case? That I will cover in detail. In last part, we have covered the basics of a crane load and how we can apply this as a moving load on a gantry girder. In this 54-meter long warehouse, a 20-ton overhead crane is supported on couple of gantry girder, which I have modeled with user-defined I section. It is supported by the column using few brackets. In this PB structure, tapered columns are used. Use of stepped column with higher depth below the girder is also quite common. To apply this crane load at different locations, we have calculated the maximum static wheel load, which is 160 kN for each wheel, and defined this under vehicle definition with proper load, axle distance and width. Then this load is applied on the gantry at fixed interval of 1 meter. For load application, total number of generated load case, initial location of the rear right wheel and load increment values are required. How these are calculated based on the crane data and position, that is already covered in part 5. Anyway, we can use the analysis result of this generated vertical moving load case, like the maximum bending or deflection value for the design of gantry girder, but it is not suggested as the results are not realistic. When a loaded crane is in static condition, then we can easily assume the wheel load as vertical load, but when it starts to move in the longitudinal or transverse direction, few additional load components are imposed on the gantry, like a horizontal load or an axial thrust generated due to the movement of crane. We need to consider this horizontal component during design, else the section designed with only vertical load might not be able to handle this additional shear and axial force. Also, this gantry is not an isolated component, rather it is a part of the entire structure which supports the crane and transfers the load to the column. When the structure is subjected to an earthquake, along with all other structural components, gantry girder also moves laterally. For realistic design of all the components, including column, bracket and gantry, we need to combine this crane load with other gravity and lateral load case. In IS 800-2007 under Table 4, could suggest combining the crane load with dead, live and lateral load using a predefined factor. These load combination rules are already implemented in STAAD. Under auto load combination, there is a separate category to combine crane load with other load case. How we can use the factors for combination of moving load with other load, that I will cover in detail. Let's start with the horizontal and axial load component. Under vehicle definition, we can only define a load in the vertical direction. No option is available to add a load from any other direction. Also, in the load generation window, there is no additional option for horizontal load. So, we cannot include any horizontal load along with vertical moving load using the default option. That doesn't mean it is impossible. There are multiple options available to add a horizontal moving load. I'll cover a couple of methods in this video. Most advanced and automated method of moving load generation will be covered later. Normally, 10 to 20% of total vertical load is applied in the horizontal direction and 5 to 10% load as an axial thrust. To define this, we can use a feature of STAAD, Notional Load. Well, this is not implemented for moving load generation. Rather, it is meant for stability analysis of steel structure. In AISC 360 under Chapter C, could suggest performing direct analysis for steel structure, and notional load is used for that. Also, it is used for stability analysis as per IS 800-2007, clause 4.3.6 and EC3 code. Notional load is nothing but a factored horizontal load applied at a node, intensity of which depends on a vertical load. For example, if a 100 kN vertical load is applied at a node, using notional load factor 0.2 in X and 0.05 in Z, we can apply a 20 kN load in X direction and 5 kN load in Z direction. We need similar type of load component for moving load case, right? That's why we can use this notional load feature for the generation of horizontal moving load. It's just an alternative approach. Entire load generation process is a bit complicated. Also, there are few limitations which we need to consider during modeling, else the result will be erroneous. Notional load depends on the intensity and location of a vertical load. Before analysis, program need the load detail, so it must be defined under a primary load case where the loads are combined prior to analysis. Combination loads are not suitable for this. If you don't know the difference between a repeat load and a load combination, you can check my previous video on this topic. For stability analysis, normally we combine a dead and live load case under a repeat load, add this notional load under that load case from a specific horizontal direction. Load factor is specified as per the design guide. If you need more information about notional load, let me know in the comments. Same logic can be followed for moving load case, with one change. It is not possible to add a notional load under any generated load case. Moving load is a generated load which does not even exist before analysis. During analysis, based on the vehicle definition and load generation data, program generate this load. To combine a horizontal notional load with vertical moving load, we need to create a new primary load case for each generated moving load and add this notional load. For this structure, we have generated 50 moving load case from load 5 to 54, and under each load case, 4 wheel loads are applied on the girder at a specific location. To apply a horizontal load at each wheel location, we need 50 new primary load case, and under each primary load, we need to define a notional load. For example, I want to add 20% horizontal load with the first moving load. Under a new primary load, we can add a notional load with load 5 from X direction, factor 0.2. For second moving load or load case 6, we need to repeat the same process. This time, load 6 is used. Basically, we need to generate same number of primary load as moving load case, then call each moving load under notional load. This is for X direction. Similarly, we can create another notional load under same primary load case for Z direction. This time, the factor will be different. 0.05 or 5% of vertical load is applied as an axial thrust. Under each load case, 2 loads are added where 160 kN vertical crane load at a static location is converted into 32 kN load in X and 8 kN load in Z direction. This is repeated till the crane load reach the end point. There is one problem. If we try to add this notional load from the load page under repeat load category, there is no moving load case available for selection. Only dead, live and seismic loads are available. Moving load is generated during analysis, so load 5 to 54 are not yet present in the model, and it is not possible to add a notional load with any moving load case from the UI. We need to add this from the input editor. Consider this model. No notional load is generated yet. I want to add a notional load for load case 5. For that, simply create a new primary load case with any name and default load type. I prefer to generate the load starting from 100. If required, we can expand this moving load later. Next, open the input editor. Under load case 100, add notional load. Correct syntax will be suggested here. In the next line, first provide the vertical load case number, which is 5, then the direction of load, x, and finally the factor, 0.2. This will create a horizontal notional load in x with intensity 32 kN. Copy and paste this line. This time we'll change the load direction to z and factor to 0.05. That completes the notional load generation in the horizontal and axial direction. It is not yet ready for analysis. Under this primary load case, only the notional loads are applied, which means only a horizontal and axial load is applied on the gantry girder. We need to add the actual vertical load along with this notional load. To add any generated load, we can use a repeat load. Add this before the notional load command. Then specify the vertical moving load, which is 5, and the load factor, which is 1. With this, our load application is complete. This repeat load adds a vertical wheel load, and this notional load generates a horizontal and axial load. Combinedly, this load case replicate a moving load from all three directions. If we want to combine this load with any other load case, we can simply define that load case number and combination factor along with this moving load. Say we want to combine the moving load case with 1.5 dead load. For that, define the load number after moving load, which is 3, and factor as 1.5. This will combine the moving load with the dead load case. Similarly, we can combine it with seismic load using a factor 1.2. This load case now represents a combined moving load in 3 axes with dead and lateral load. Using this approach, we can combine any moving load case with other load along with loads in the horizontal direction. This process is time consuming and kind of boring, right? If there are 50 moving load case, we need to add 50 new load case manually, one by one, from the input editor, which will obviously take huge amount of time. How about an automated way? Well, for any repetitive and time-consuming task, I always prefer this type of automation using OpenSTAAD function with any programming language like VBA or Python. I have developed this user tool to bypass all this manual effort. We can simply define the primary load case number, which we want to combine with the moving load case, say dead load and live load with factor 1.5. Next, define the start and end load case number of the moving load, 5 to 54. Combination factor of the moving load, which is 1 or 1.05. Finally, the percentage factor of horizontal and axial load. That's it. Nothing else is required. I'll use the same model for load generation without any notional load. Simply click on this Generate tab. See? 50 new loads are now added to the model, starting from 100. Each primary load includes a repeat load, where the moving load case is combined with the dead and live load. Couple of notional load with same moving load case from x and z direction with factor 0.2 and 0.05. I have also included the load information in the title. It is easy to understand during editing or result interpretation. Using this type of automation, we can easily minimize our manual effort. Just create the primary and moving load case, then use this tool to generate rest of the combination load and load in the horizontal direction. Now we can use the analysis result of this combined load for column and gantry girder design. Though this method seems okay, there are few points that we need to keep in mind. We can only generate a notional load in the global direction. For this model, Global X and Z direction are same as the horizontal and axial load direction. But if the model is inclined to the global plane, then we cannot use this feature for load generation. Also, notional load is generated at a node. If no node is present at the location, then load is applied at the nearest node. Check this load case. For this load, wheel loads are applied on the girder at some intermediate point. No node is present at this location. When this load is combined under a primary load case using notional load, horizontal loads are applied at the nearest node, not at this wheel location. Intensity of the load is also different from our assumption. Program internally calculates the load value at each node based on the distance and then apply it. If we want to use this method, then for more accurate result, we need to divide the gantry girder in such a way at each wheel location there is a node present on the member. For such case, notional load will be applied at that node with correct load intensity. For this model, load increment value is 1 meter, so we need to divide each gantry girder at 1 meter interval. This is not a good solution, as during design parameter assignment, we need to define extra parameter like dj or effective length parameters to define the entire length of unsupported member. That's why I don't prefer this approach. There is an easier method using which we can apply a horizontal and axial moving load in any global or local axis without any member division. Also, we can use the autoload combination factor to combine the moving load with other primary load case as defined under table 4 of IS 800-2007. That I'll cover in the next video. Keep watching.